Okay, so we are in an introduction to statistical learning, question 14, parts A through G, and this video will be done in Python. I've already made one for R, so check out the one that is most applicable. So this has A through G parts, so we're not going to look at all of the questions all at the beginning here, so we'll just get into one at a time. So the first thing that we need to do is to generate some fake data, okay? And so that's what we are doing here. We have variables x1, okay, which is a uniform distribution, x2, which is a function of x1, right? And then y, which of course is a function of both x1 and x2. Okay? And so now it asks us to write the linear model for this and to say what the coefficients are, what the values of the coefficients. So here is the formula for the linear model, right? Beta 1 times x1, beta 2 times x2, dot, dot, dot. Where beta naught is 2, right, the intercept. Beta 1 is also 2. And then beta 2 is 3 and not 0.3. And I'm going to come back to that in just a second here. And then the epsilon term here is just this part right here. It's just adding random noise with a random normal variable with mean 0, standard deviation or variance 1. Okay. So why is beta 2 3 here? So recall that the beta coefficient for a given variable, call it x little p, is what happens, is the change in the y in the outcome when xp goes up by 1 unit, okay, by 1. Okay, but here we see that x2 has been divided by 10, right? So it's on the scale of 1/10 of 1. Okay, so in order to get the correct beta 2 coefficient, we actually need to multiply this value by 10, right? Because that would represent what happens when x2 goes up by a full unit, by 1. Okay. All right. So now we want to, so we created this data, and remember that x2 is a function of x1. So we want to look at the correlation between them. So here's the correlation, 0.77, and here's a scatter plot of the data, x1 on the x-axis, x2 on the y-axis. Okay. So now we're going to fit a linear model to all of this data, and we're going to talk about it a little bit, okay? So, or I guess I've already ran that. So let's come down here to the coefficient table, and there's some interesting things here, okay? So let's first look at the p-values here, okay? So actually both of these are reasonably low. I guess that's good. We know that they should not, we know that that beta 1 and beta 2, the coefficients for x1 and x2, are not 0, right? Because we made the data so that they're not 0. And the p-values may kind of reflect that. You might expect it to be lower p-values, but that's fine. But here's our estimates. And notice that the estimates are not that close for x1 and x2. The intercept, the constant here, is close to what it should be, and that's fine. But x1 and x2 are not very close to what we think that they should be, again, which should be 2 and 3. And we will discover that the reason for this is because x1 and x2 are highly correlated, as we've already seen, right? They are highly collinear, okay? And these linear models have a difficult time getting good estimates for highly collinear data, okay? All right. So now we're going to, instead of regressing y on x1 and x2, we'll just regress it on one of the variables, in this case x1, and then we'll also look at x2. And when we run this, so here's our data, or here's our output, now we get a very low p-value, right, which we should get because we know that the beta coefficient for x1 is not 0, and the estimate is pretty close to what it should be, about 2. All right. We do the same now for x2, and again we find a pretty similar result. We find that a very significant p-value. So and we also find that the estimate is pretty close to what we know it should be, and it should be about 3. Okay, so now what we've seen is that when we regress these collinear variable, or when we've regressed y on both of these collinear variables, our estimates are pretty wonky. But when we regress on just one of the variables, then we get reasonable estimates. We get what we expect to find, okay? And so part F asks us if we see a contradiction here and to explain our answer. So what I just explained is the possible contradiction that the question alludes to, but I'm not really sure that it should be considered a contradiction, because we know why it's arising. It's arising because of these collinear variables. So whether or not we label that a contradiction, I guess, is really just a matter of taste. But the important part is that we recognize the effect of adding these collinear variables to the model. Okay, so now everything we just did, we're going to do it again, but this time with one new data point. And that new data point is given by x1 equals 0.1, x2 equals 0.8, or y equals 6. Okay, so we run that data. So now we have new x1, x2, and y, and so we're going to do everything again. So the first thing we'll do is to look at the correlation. Okay, so here's the new data. Here's our new data point up here. Okay, and here's our correlation. Okay, it's 0.68. Now that is a reduction from before we added this weird one, this new data point, where it was about 0.77. Okay, there we go. Okay, so we've had a reduction in the correlation, which we should get, right, because we have this new data point that doesn't fall in line with the pattern. Okay, so again, we're going to do regression on both variables, which are collinear. Okay, and we're going to look at the results, and then we're also asked to determine, given this regression, if the new data point is an outlier and if it is exerting a lot of influence, or I guess it just asks for leverage, but we'll address leverage and how much influence it's having on the fit, okay, as well as we're capable of at this point. So here's our regression coefficient table, and again, we have weird results, okay, that aren't really that much different from the first one. Okay, and actually, let me just run this again just to make sure I've done this correctly. Okay. Okay. So here we have our regression coefficients. We see that the second one is kind of close to our estimate. The first one, not really. Okay, which is fine. But so let's try to decide if this new point is an outlier. And so these first two plots should give us an indication if there's any outliers. I think that this might be the point right here. I wish we could. I wish I labeled them, but I didn't. But it's hard to say that it's really an outlier. But we look at its potential as influencing the fit of everything, and we see that it may not have huge leverage. It has kind of a lot of leverage, kind of middling leverage, but the residual is quite large, and so it might be exerting quite a bit of influence on the fit of the model. Okay. So now we do this. Now we regress y on just x1. We run all of that. Okay. So remember that the regression coefficient for x1 should be 2, and before we added the weird data point, we did get a fairly close estimate, and now we are not that close. It's because this outlying data point, or this weird data point, doesn't really fit the pattern that well. Right? It was generated outside of how we actually generated that data. Okay. So it looks like it probably is an outlier. There it is right there. There it is right there. And it also has quite a bit of leverage. Now it's a high leverage point, but its residual is kind of middling. So again, whether or not it's exerting a lot of influence on the fit of the model, it may or may not. There are more rigorous ways of telling, but I don't think that the book has talked about those yet. Okay. And now finally for x2, we do the same thing for x2 and go through the same song and dance. And here we see that that it's maybe exerting a lot of influence. We have middling leverage, low leverage, and high residual. Okay. So anyway, that is it for this one.